Okay, the next two worksheets are just about analyzing data that might be given to you on any sort of AP problem. The position of a particle moving along the x-axis given at various times shown, and the data has been plotted. So the first thing is just to try to connect with a smooth curve. And this is only so you have a visual of this. So think of this more like a strategy rather than something that they would actually have you do. You wouldn't actually connect dots, but if you had dots plotted and you can kind of perceive some sort of smooth connection, it's logical that there would probably be a smoothness to this since you'd have a single curve rather than have instantaneous rates of change. Remember that instantaneous rate of change, or those cusps usually happen because of some sort of circumstance that was artificial. But if things are proceeding very normally, you can expect some sort of curve for this. So then it says find an estimate for the velocity of the particle at t equals 4. Well, what would that be at t equals 4? What are we looking for? So this is a graph of position versus time.
The derivative.
Yes. So it's the derivative. So as the first derivative, what is the visual translation of that on the graph right here? What is a first derivative? What do we know a first derivative is?
It's the slope of the tangent.
It's the slope of the tangent line. So rather than look at that and guesstimate by just saying that, we have some information around it, and we're going to use that to the best that we can. We have the slope of this and the slope of this.
Right.
So one way to do it is actually just to do the slope of these 2 points. But what I prefer instead of that, because that ignores the point in between, is to average the slopes of this and this. So what I'm going to do is I'm going to do the average of, let's do the average of s of 2, or s of 4 minus s of 2 over 4 minus 2, comma, s of 6 minus s of 4 over 6 minus 4. And I'm writing it like that because that just shows what I'm actually kind of calculating. You guys know how to find an average, but I'm going to keep it in this notation for now. So the average, s of 4 is 4, and s of 2 is 2. So this is 4 minus 2.
Which is 2 over 2, which is 1.
Over 4 minus 2. And then, sorry, 6 minus 4 is, I'm looking actually at the charts, that's 3 over 2. So it's the average of 1 and 3 halves, which is 2 halves and 3 halves, which is 2 halves would be the average. I'm going to write this in kind of this notation. Say the average of 1 is 4 fourths and 6 fourths. So the average of 4 fourths and 6 fourths would be
5 fourths.
5 fourths. So that's an estimate for the velocity at t equals 4, 1 and a fourth. Estimate for the velocity of the particle at t equals 10 is going to be about the same thing. Now, you can look at that and say, well, that looks like it's going to be a maximum, so it looks like it's going to be v equals 0. And you can make a case for that because it looks like a turning point, but let's just be sure and do kind of an average of this slope and this slope. So same idea. I'm going to do s of 12 minus s of 10 over 2. And then I'm going to look at s of 10 minus s of 8 over 2. So s of 10 is 12 and s of 8 is 1. So this is going to be the average of, keep putting ag, average of 1/2 and, what's 10? Yep. Or sorry, no, my bad. 12 minus 10 was -2. So it's the average of -2 over 2 and the average of, and 1/2. So for this one, I'm just going to add and divide by 2. Yeah. So this is -1 and 1/2. So this is -1/2 divided by 2, or yeah, -1/4. So that's a better average than just saying 0. I mean, -1/4 is a very, very, very relatively flat slope, but it's not quite 0, obviously. Okay. Now, that's average velocity, or estimate for velocity at a point. And I want to kind of emphasize this. Right here, when I say estimate for the velocity and estimate for the velocity, what I'm looking at for both of these is an instantaneous. So I'm going to kind of try to mark that a little bit clearly, that this is an instantaneous, which means derivative. But 3 is asking a very different question. It's asking the average velocity on an interval 0 to 16. So an average velocity on an interval actually has nothing to do with what happens in the middle. It has everything to do with what's happening, the slope of the line if I were to connect those. So t equals 0 is here, t equals 16 is here. Let's do a visual representation of what that looks like. If I can draw a straight line. So it's the slope of that purple line, and that's just going to be s of 16 minus s of 0 over 16 minus 0, which is 9 minus 5 over 16, or 1/4. And that would be the first part on 16, well, 6 to 14, same thing. S of 14 minus S of 6 over 14 minus 6 would be 8. And S of 14 is 6, S of 6 is 7, so 6 minus 7 over 8, and that would be negative 1/8. And that should match what you do when you draw it. If I connected 14 to t equals 6, which would be, I'm running out of colors here, we'll make this gray. Yeah, it's a negative slope. It's kind of barely a negative slope, but you can see it connecting right there. And finally, on what intervals does it appear that the velocity of the particle is positive? So velocity of the particle is positive. Velocity, again, is the derivative. Basically, it's asking not only where's the velocity of the particle, it's actually asking where's the graph of s increasing, right? Increasing on s means that s prime is positive. And if I go back to that table that we did, s increasing means s prime, which is equal to v, is positive. And then just for kicks, what would it be for s to be concave up? Yeah, increasing. And then s double prime equals v prime, which equals acceleration, would be positive. Typically, we don't talk about that with velocity acceleration. We just talk about that with f prime, and f double prime. But having this down, and if there's something that, Zach, if you want to put in your note cards one day, like that would be a big one. And then just, I would write one of them down. And, like, I wouldn't write both positive and negative down. I wouldn't write both, like, increasing and concave down. I just do one of them, and then the other one's the other one. So the graph of s is increasing on, let's say, from 0 to, or no, it's not 0, from t equals 2 to 10, and then 14 to 20, and then 22 to, probably should stop.
To 24 or to infinity?
Well, it just depends on what the question actually would probably have to be more specific and tell you, like the graph would have to tell you if this is a determination, but for the purposes of this one, I would say 22 to 24, because that's just, there's nothing saying that it goes on forever at that point. We just have the graph that we see.
The fact that you drew an arrow.
Besides the fact that I drew an arrow. I would, I think I would accept 22 to infinity just fine. Okay, I'm going to take a break for a second while I pull up the other one and pause this. Now, all right, second one talks about a car traveling a straight line for 1 hour. It wants you to produce a graph of the velocity function. It gives you the velocity at these different points. So not only should you graph this, which is going to be a little bit painstaking, 0, 0, 0.110, 0.220, then we go to 40, then we go to 60, then back down to 50, then to 40, then to 35, then to 40, and then to 50, and then all the way to 65. So it is possible to produce somewhat of a smooth curve for this. When I told you guys to graph each eta, that just means whenever you do a turning point, stop and take a break in your pencil. This is about what I would get for something that looks like this. This is different from the previous problem because this is a graph of velocity versus time. So what makes it interesting is that you both can pick up acceleration from this by doing a first derivative at any point, but you can also talk about the area under the curve. And the area under the curve would be the accumulated velocity, in other words, the position. So find the intervals over which the acceleration is positive. This is about the same questions you had before. Acceleration is positive when V prime of t, or V of t is what?
When V of t is increasing.
Increasing.
That's what I was
So
gonna say, the word was not.
when V of t is increasing, so that would be on 0 to 0.4 and from 0.7 to 1. And we're just going to stop there because it says actually in 1 hour. So that little arrow I drew at the end is probably not good, but whatever. Average acceleration of the car over the interval 0 to 0.4. So I can go from 0 to 0.4, and we're just going to do velocity at 0.4 minus velocity at 0 over 0.4 minus 0. So 60 minus 0 over 0.4, which is the same as 600 over 4, or 150. And I can get a unit down on this. This would be miles per hour. And I'm checking the kind of units on this. We're just kind of deriving with this. So this is going to be miles per hour squared, which is okay for us. You may want to convert, if you were actually communicating that to someone, between miles per hour squared and miles per hour per second. So if you were to do that conversion, you just have to take that last miles per hour and do a multiplier on that. Remember, you would kind of write it like this if you were going dimensional analysis, miles per hour like that, and then do 1 hour over 3,600 seconds. That way your hours cancel and you get miles per hour per second, which is inadvertently the same as miles per second per hour. What does the integral signify? The integral from 0 to 1. People listening, you guys should be thinking about this too. What does the integral signify in this problem between 0 and 1?
The position.
So position change, that's important right there. It's position change from 0. So one of the things you have to do when you do this integral is, because it's position change, my position at time equals 1 may not be that integral. It may be the integral plus an initial thing. So I want to kind of go back to the most important formula in calculus. S of 1 would be equal to S of 0 plus the integral from 0 to 1 of V of t dt. So this is the position change, but it's not necessarily where it lands. So when you actually just talk about the integral, you have to talk about its change in position, or change in number of miles, if you want to get very specific. When do I use the right one? When a question asks, like, what is the position at time equals 1, and then buried in the original problem it would say, like, it starts at a position of whatever, and it would be in the text of the problem. It wouldn't be in the graph. So you can see how that can be really tricky, that it would give that to you. It doesn't say anything about where it starts or anything, so but the question doesn't actually ask you for S of 1, but it's worth pointing out. Okay, approximate this using RRAM and the trapezoidal rule with 5 subintervals. So 5 subintervals, if you want to draw the trapezoidal, we're going here to here, then here to here, then here to here, then here to here, and then there to there. Those are your trapezoids. Again, I tend to be visual. I'd ask you to do, RRAM and the trapezoidal. Sorry, we are doing RRAM too. So let's start with RRAM. RRAM is, the base is the same, and so the heights of each of the rectangles is the rightmost one. So whatever the height at point 2 is, 20 plus 60 plus 40 plus 40 plus 65. And we can do this. It's 1/5 times 120, 160, 225, which is 45 miles. I'm going to move this over to the side so I can use this space here. And then trapezoidal is a little more complex. I would probably, just to be honest with you guys at this point, I would probably do LRAM and then average them, because it's just going to be an easier process if I've already figured out what RRAM is. So let's just go ahead and figure out what LRAM is. It's 0.2, and then I shift everything over. And if you got LRAM and RRAM wrong, at least your trapezoidal would be correct. So 0 plus 20 plus 60 plus 40 plus 40. So that is 120, 160, and 1/5 of 160 is 32 miles. So trap is going to be equal to the average of 45 and 32, or 77 over 2, or 38.5 miles. Is that right? 6.5, 6.5, yep. Okay, and then finally approximate the acceleration at t is equal to 0.8. I don't know the acceleration at t equals 0.8. I know, let me kind of erase these lines. Guys, just stick with me for a little bit longer. So if I go t equals 0.8, what I can do is, going on this graph, I can figure out what this slope is and what this slope is, because acceleration is the instantaneous rate of change at that point, but I don't know that, so I have to average the two around it. So I need to do the average of, yeah. So we do the average of v of 0.9 minus velocity at 0.8 over 0.1, and then the velocity at 0.8 minus the velocity at 0.7 over 0.1.
Mr. L, is RAM right to left?
RAM means the top right corner of the rectangle is the point. What?
If you think about just the values.
Yeah, it's the right one. So you're shifting it to the right. So RAM uses this, 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 and this, because your rectangles are like that. So it's the top right one, and LRAM uses the other ones. LRAM uses this, this,
RAM, if you
this.
did for that one, would it be with the first number? Yeah, it would be 0.
Yeah, we did LRAM. We did it right here. Because if you're going to figure out trapezoidal, it's probably easier just to figure out LRAM and average them. Okay, anyway, back to this 0.9. So this is 50 minus 40 over 0.1. And this is 40 minus 35 over 0.1. So 100 over 0.1 is 100, or 10 over 0.1 is 100, and 5 over 0.1 is 50.
75.
So the average is, so we'll say average acceleration, or not the acceleration, I'm just going to say 75, and we're going to miles per hour squared. Which again, if you wanted to convert to miles per hour per second, you'd have to multiply by 1 over 3,600. Okay, we're done.